what is the value of, not sure how I should say this, of this thing we have here. So it's 5 on top and 3 in the bottom. What is this, and how do we read this out? Well, here's the quick answer. This is the combination. By the combination, I mean there's the number of ways you could choose 3 things out of 5 things. And the way I would read it is, what is the value of 5 choose 3? So you have 5 exams this semester. We are in, what's the month? It's February right now. We're in the spring semester. And you either have to take the exam in May or in August. So you say, okay, I'm going to take the first 3 exams and delay the other 2 to August. I want you to notice that by choosing 3 exams, you're not choosing 2 exams. So in a sense, we could, I would like to say intuitively, conclude that 5 choose 2 is equal to 5 choose 3, because choosing 3 items is equivalent to not choosing 2 items. Now here I'm trying to build the intuition basically. That's one way. Another way could be this. That's 2. That's 3. That's 4. That's 5. That's 6. I hope you're counting. That's 7. That's 8. Now finally, that's 9. And I think I forgot one of them. So in the end, they're going to be 10. You have to trust me on this. I've made some sort of mistake here, but just let it be. So you have 10 ways to count them. And let's say you don't have 10 ways to count them. The only reason I'm doing this, and the only reason I'm purposefully spending time on this, is to say that it takes time. And this is obviously not the best way to get the job done. I imagine you were agreeing with me subconsciously on this fact while watching me count different combinations of exams. So what is the better way? What is the better way? We don't like this. So we're not going to spend our time counting. Imagine if I tell you how many ways you can choose 7 items out of 17. Okay, I mean, using the same algorithm that we would try to implement now, it would still take some time, because I imagine on the exam you won't have any calculators, you won't have anything to use. But at least this improves the method with which you can obtain your value for this expression, and that is the Pascal triangle. And it looks like I memorized it. Looks like I'm just writing it down. But effectively, what I've been doing is something that's very interesting. So here's how you should write the Pascal's triangle. Of course, it goes on and on. You start with 1, and you always have 1s on the sides, in a sense. On the first row, you have 1 element. On the second row, you have 2. The third one, you have 3. The fourth one, you have 4. and so on. How do you figure out that this is 2 or that that is 3 or that that is 3? It's simple. You take the upper two neighbors and you add them to get the number. Perhaps it would be a good exercise to try and write maybe the first 10 rows of Pascal's triangle. And okay, this is good. It looks nice and it's a nice triangle. What do we do with it? Here's what we do. So we start counting from 0. I imagine the computer scientists in the audience would really fancy that. And so on and so forth. And let it be publicly stated and known that we are looking to compute n choose k. By the way, if we were to generalize this for n, we would say that n choose 2 is equal to n choose n minus 2, because if I choose 2 things out of n things, it's the same thing as not choosing n minus 2 things out of n things. There's also some quote that I like to use in my practical life, which doesn't have anything to do with mathematics. And it says that everything you say yes to, you say no to every single other thing you could have done. And since we have finitely many time in this universe, you should think about what you say yes to. So I'm glad you said yes to watching this video tutorial. This makes me very happy. And I'm pretty sure you made the right choice. If you would like to generalize this even more, I would jump from k and from 2 to k. So if I choose any k elements out of a group of n elements, it's the same thing as not choosing n minus k elements out of a group of n elements. And k could be thought of to be less than or equal to n, in a sense, because it doesn't make sense really if you want to choose, let's say, 7 items out of 6. So if I make this bigger than n, let's say 7 and this is 6, you can't choose 7 items out of 6. So in the end, it will be 0. I mean, it does make sense. The answer will be 0, but we're not interested in such combinations. So this is a combination. Okay, so back here, we would like to find this value. How do we find it? Well, it's not that difficult. So you always start counting the indices. This is your k. It doesn't matter if you count from left or from right. Of course, you could go on. We're interested in the case where n is equal to 5. So let us take a look at that. We are interested in this row. And we are looking at the value for 3, which in a sense is the 4th element. Sorry, this is k. And I won't do this for all indices, but just for the 5th row, well, the 6th row, it's a fix because you start counting from 0. I'll start counting from right to left instead of counting from left to right. I think the camera is switched, so please forgive me. I say right and it's on your left. Or, I mean, you don't have to forgive me. You see how it turns out that from left to right, it doesn't matter. If you take a look at it, there's the sense of symmetry. So there's the 3 and 3, there's the 4, 6, 4, there's the 5, 10, 10, 5. This is why it doesn't matter from left or right. And in the same sense, in the same exact sense, it obeys this intuition. So if you pick 4 elements, it should be the same thing as not picking one element out of 5 elements, and so on and so forth. So this is really the structure of the Pascal's triangle. On the surface, the question is asking you to find a value of 5, choose 3. And I imagine you could very easily compute that if you have a calculator. Perhaps a little bit more challenging to do if you don't have a calculator. But definitely very enjoyable if you know what the Pascal triangle is and you know how to utilize it. So that was really the goal of this tutorial. It was not to talk about 5, choose 3 in particular, but to give you and to provide a method with which you can compute all combinations. And this will be relevant when you're trying to expand a term which has many, a polynomial, for example, of the form x plus y to the n. Because as it turns out, by something called the binomial theorem, this is going to be equal to the following. But this is, of course, absolutely irrelevant to the content of this. Okay, I wouldn't say absolutely. I would say the relevance here comes from the n choose k. So if you're computing, for example, x plus 7 to the power of 12, it is very handy. It's very handy and it's very useful in that very specific sense. Now, we still have not answered the question. Well, I imagine you already have an answer for it. So you would like n to be 5 and k to be 3. You could either choose this 10 or choose the other 10. So that is really up to you. I'll leave that for you to decide.